Hello, everybody. Welcome to the very first SMPTE webcast of 2019. This is a SMPTE Standards webcast, and we have quite an audience, and I appreciate everybody joining us, especially on such short notice. The topic today is building scalable media systems using SMPTE 2110 and JDM TR-1001-1. You can see our speaker's name is John Myatt, and I'll introduce him momentarily. First, I am Joel Welch, SMPTE's Director of Education. If I can ever do anything for you in terms of education, please let me know. I'm happy to help. If this is your first time with SMPTE Standards webcast, they're a series of usually 1 hour, maybe sometimes 90 minutes. It depends on the amount of content and the number of questions. They are interactive, or at least we hope they're interactive, but that depends a lot on our guests, that is you. And we do ask that you pose questions to our speaker, and especially oral questions. Oral questions take priority. They go to the top of the question queue, but if you don't have a microphone or you prefer not to ask a question via your voice, you can always type them into the question box, and I see we have a couple of questions, and one of them is, how do we submit oral questions if we're all muted? That's a very good question, and here's how you do it. You type in the question box, I have an oral question. I will unmute you at the appropriate time. You can speak directly to your presenter, and when your question is completed, I will remute you and take it from there. So I hope that helps, and as I said, if you don't have a microphone or prefer text questions, have at it in the question box you should see in the control panel. Standards webcasts are free to everybody, and the on-demand video is also free because we do record them for on-demand viewing. They'll be available on SMPTE.org and YouTube, and we'll send information about that a little bit later. Please tell others about SMPTE webcasts if you use social media, tweet, post on your Facebook, post on Instagram, whatever. The handle is at SMPTE Connect, and the hashtag is hashtag SMPTE Webcast. Let's see. Also, there will be a PDF of the slides presented today provided to you in exchange for your feedback about the webcast. That information is very important to making sure that we are continuing to do what you need us to do in education, and your experience in the webcast is, we want to know about it. It's very important. So, your speaker today, as I said, is Mr. John Myatt. He is CTO of Networking and Infrastructure at Imagine Communications. John, you seem to have control. The floor is yours.
Thank you, Joel. Hope you can hear me okay.
We hear you very well.
All right. Amazing how this internet thing works. Maybe we should use it for television production. The topic, as you saw, was about how to use 2110 and the new JDM Technical Recommendation 1001 to build scalable television facilities. And so the first thing to know about SMPTE 2110 is that it's done. All the core parts have been published. Some of them have been published for quite a while. Like any family of standards within SMPTE, there's always some more parts that are on the go. So in addition to the core video, audio, timing, and so forth standards that are all published, there is a compressed video essence standard that's in process in the committees. There's also a 2022-8, which says how you would integrate 2022-6 with the 2110 family. That is in the queue, that is near the completion stage of the process. Let's say I would expect to see that come out real soon. In addition to the SMPTE work that goes on, the Advanced Media Workflow Association also is deeply involved in the applications for this technology. In particular, the API or the interface specs that describe how a controller would control these devices or how a device would find its home in the network. Those specifications are published by the Advanced Media Workflow Association, and they have the rank of stable, which is has a meaning in the AMWA nomenclature of a document which has been unchanged for quite some time and is generally regarded as trustworthy and stable. And of course, the JTNM technical recommendation was just published. So I'm going to start out with an overview of SMPTE 2110. This might be the fastest overview you've ever had, but I wanted to at least level set that everyone is up to the same place in the history of all this. SMPTE 2110-20 is about uncompressed video, and so it says how to form an IP flow that contains active image area. So in the old days when there were CRTs, we had to leave time for the retrace and the vertical blanking and so forth, but really hopefully CRTs are mostly behind us now, and so in the new standards we're not sending blanking samples. We only send the active image area, so the 1920 by 1080 or the 2160 by 3840, active image. We don't send all the samples that don't contain video. And this is helpful. This actually saves in North America about 16% of the bandwidth, and in Europe it saves quite a bit more, almost 30%. The 2110-20 standard was written to be, as much as anything could be, to be sort of future-proof. So while we're implementing UHD today, most of us, and 8K is in demonstrations, and I think somebody actually talks about 16K now, we decided that we would just support right from the get-go up to 32K by 32K. So we don't have to revisit this document to add more image sizes. Also supports all the different color methodologies that are in use today. So the YCBCR, RGB, XYZ, so forth, and all the different color primaries as well. So the 709 and 2020 and 2100 and P3, there's a huge variety of defined things that are supported in 2110, and also a whole range of bit depth and sampling parameters. And of course, like any modern video standard, we have support in there for the HDR formats, for the PQ and the HLG, and of course the one we call SDR, which is standard dynamic range, all supported in the document as published. So hopefully we don't have to reopen the can on 2110-20 anytime soon. 2110-30 for audio is entirely based on AES 67. So the AES spent a long time working through all of the different issues in the audio industry. They came up with AES 67. It's a great standard. And so we said, well, gee, why would we do anything different? So 2110-30 is a very short spec because it says use AES 67. And then it does have a few constraints and a few, here's how you advertise it in the STP and so forth. But fundamentally, 2110-30 is, compatible to and with AES 67, and that's on purpose because the audio industry has spent a lot of time getting that right. Of course, 2110-30 and AES 67 allow a lot of different styles of audio, so we are very careful to define that, all devices have to support 48 kilohertz sampling. All devices have to support 1 millisecond packet time. All devices have to support up to 8 channels per stream. And all devices have to support 16 and 24-bit depth. But there's many other things that are defined that you could do if you are, in fact, trying to do a specialty application. So, as in all things, read the spec carefully if you're out in that fringe. Now, non-PCM audio is fairly common in television. Dolby E is a very common use case. Dolby AC3 is a common use case. But many of the new object audio systems also have audio metadata or other things that are formatted in an AES3 carrier, but are not really, strictly speaking, PCM audio. So 211030, of course, AES67, only defines PCM audio. So for non-PCM audio, we have a document 2110-31, which provides a way to transparently send an AES3 pipe over an IP network. So it can handle all of the non-PCM audio cases that are mapped into AES3, but it can also handle AES3 applications that use the user bits or that use the C bits or the V bits in some novel way. Things are accommodated in the 2110-31 standard. So it's provides a operational flexibility to do that. Of course, AES3 is always got two things inside. 2110-31 always has a multiple of two things inside. You can bundle several together, but as you'd expect, it's always a stereo kind of pair, or at least two channels. They don't have to be a stereo pair. Now, 2110-40 is our new standard for ancillary data transport. So all of the things that over the years people have put into the SDI ancillary data system, we wanted to provide a generalized way to accommodate all of those in IP. And so there is a single defined thing, 2110-40, and a related IETF document, RFC 8331, which describe how to wrap ancillary data packets in IP, transport them and timestamp them in a 2110 environment. This is all, again, published, and this in particular will probably be one of the focal items at the upcoming interop events this spring, or sort of interop testing of this ANS data transport. We've done, as you know, a lot of work in video and audio and some work in the ANS data. I look forward to everyone bringing their ANS data implementations this spring, and we can test them all against each other. So 2110-10, which I saved for last, is really the critical bit because it describes how all these parts stay in sync. Now, on SDI, it was pretty easy because everything was embedded together in one wire. It was all tightly coupled together from a timing perspective. So if you got an SDI, you could assume that the video and the audio and the ANS data in there were all stapled together time-wise. And if they weren't, then you went and looked at who sent it to you. Here, we're putting each of the essences into a different IP flow. So while they're in a common IP network, they can have different timing. They can be, one can be a little late, one can be a little early. So how do we keep things in lip sync? How do we put lip sync back together? The key element in 2110 is Precision Time Protocol, or PTP. Every device that does 2110 supports PTP, and so every device has a very accurate time reference and knows what time it is. So when you generate a video stream or an audio stream or a VANT stream, you put a timestamp, an RTP timestamp on every packet you generate. And those timestamps are the sampling time. So if I have video that was captured at a certain time, and I have audio that was sampled from the microphones at a certain time, those timestamps live with the essence through the network, and I can put them back together again by comparing those timestamps. And this is a key feature of 2110, because now a network user can mix and match essences from different cameras and different microphones and get them synchronized because of these timestamps. So this is the crux of the 2110 system. So before I dive on into the meat of the topic today, which is how to build scalable systems using the new tech recs, are there any core questions about 2110 itself that I can address sort of now-ish?
Well, we have a couple of questions in the queue. The first is from our guest Tucker, and Tucker says, is the 1 millisecond packet time the allowed processing delay for any device in the signal chain?
So the 1 millisecond is not a processing delay. It's simply how often do I send an audio packet. So 1 millisecond is the standard packet time, if you will, that's required for all devices to support. Many devices also support 125 microsecond packet time, and there's applications like in-ear monitoring and other things where it's actually quite important to use the shorter packet times. But yes, if you use 1 millisecond packet time, then you have at least 1 millisecond of delay because you've basically waited a millisecond to gather up 48 samples in the case of 48 kilohertz audio to put together in one packet.
Okay, let's see. We do have an oral question from Michelle. I just need to find him in the list, and I will unmute Michelle. Let's see. I'm going to scroll down through, and the list does not move very quickly, but let's see. Almost there. HIJK element. Oh, lots of people. Here we go. Michelle Prue. Michelle, I have unmuted your microphone.
Thank you. John, this is a topic that you and I have discussed before, and it has to do with RTP timestamps. You hear quite clearly, probably the most clearly I've ever seen, say that the RTP should represent the sampling time, which is great, and then we can use that to realign. But I wonder if you could comment about what happens in a downstream device that is, say, receiving a 2110 signal, processing it, and then re-injecting into the network. Is there a standardized or recommended practice for that device's handling of the timestamp?
So that actually has come up with many customer networks, that there needs to be at least a recommendation on that, and that is an active topic in the 2110-10 one-year review. So if you are passionate about that topic, and I know you are, we talk about it each week. So that actually is, there is a proposal on how to do that to preserve the sampling instant, and it's one of the topics we're addressing in the one-year review. So yes, that's an active topic in the drafting group right now, to have something like that in the revision that should come out.
Michelle says, thank you. Good answer. Let's see. Did you say that was in relation to 2110-21?
No, that's 2110-10.
Oh, okay.
We'll
because
cover that.
Our guest Gary asks, can you address 2110-21?
Okay. 2110-21 is probably could have been part of 2110-20, except that we wanted to have it a standalone document for sort of variety of practical reasons. 2110-21, it kind of adds on to -20 in that it describes the traffic pattern on the network. So it's one thing to make video and throw it on the network, but 2110-21 says you have to send it smoothly. You can't, send like a whole frame's worth of packets and then go silent for the rest of the frame time, things like that. It has a very detailed definition of the allowed traffic shape and traffic pattern for video, because these video flows are very large. An HD video flow is like 1.2 gigabits. What you might call a 3 gig flow, a 1080p flow, is really about 2.6 gigabits. So it's important to have very carefully prescribed traffic shapes for these flows, otherwise things can get ugly inside the switch. So that's the crux of -21.
Great. We have 3 questions in the queue at the moment. Actually, make that 4. We'll address these 4 if you don't mind, and then we'll move on. Our SMPTE's Standards Vice President, Mr. Bruce Devlin, asks, in the interop tests, what are the happy stable bits, and where is more work needed?
I'd say generally video has been very interoperable, and audio by and large has been very interoperable. The places where we expect, and we do have an interop event, another one coming up this spring in the late February in beautiful Houston, Texas. Where most people are now sort of focusing kind of interop activity is on, the VANCE data standard on 2110.31 has, not seen a huge amount of exercise across vendors. We didn't get to it in the previous interops particularly much. So I expect this spring we'll be focusing largely on -40, -31, and a little bit on, in the test equipment world, people have built test equipment that measures the -21, and we'll be sort of trying to harmonize among the test vendors to make sure if 3 different pieces of test equipment measure the same signal, that they produce a consistent reading about it, because that's kind of important also. So I'd say I wouldn't call those difficult bits, but they're certainly, everybody in their normal course of engineering these things kind of worked on video and audio first. And so we're going back through now and hitting all of the, the other bits, the -40, -31, and, the fine points of how to measure the timing stuff.
Awesome.
In addition, the ISO 4 and 5 are also deployed on some products, but not yet universally, and there's a lot of opportunity at these events for vendors to interop test their implementations of the ISO 4 and 5 specs against known working implementations.
Okay, and the first of the last 3 questions comes from Andrew. He asks you, can you talk about how SCTE message information is handled within 2110? Is this addressed in the ancillary data? And then he's
yeah. If you had say a SCTE 104 or a SCTE 35 trigger, normally that would be carried as a SCTE 104 message in VANCE, and so similarly in 2110 it would be carried as a SCTE 104 VANCE message wrapped in 2110.40. And the nice part is, because the VANCE is now a separate data flow, you could have a producer or consumer of those messages simply generate them onto the network with correct timestamps, instead of today where you have to have like an SDI inserter that takes the main channel feed, loops it in, adds the one more trigger, and loops it back out. Once we go to having separate flows for these VANCE signals, it really is liberating in the plant design, because you can stop looping your air chain through a bunch of inserters and simply assemble the signal you want.
Andrew says, perfect, thanks. Oleg asks, in live mode, what happens when the audio packets experience too much delay compared to the video packet?
Well, it's a lot like the situation today. If you somehow get in a situation where the audio is late, you can either delay the video to match up with the audio, which has its own cost and difficulty and annoyance factor, or you can tolerate the audio being late. But sadly, those are kind of the 2 choices today. The nice part about the 2110 system and having these timestamps is at least and you can measure how late they are. And many devices have, an amount of buffering for video and for audio. And so they have a certain capability to, match them back up. And that's actually another active topic in the 1-year review, is defining more accurate, or in more detail, how to talk about that, and how, what does play out delay mean? How long should a device wait for a late signal before it just goes anyway? Those kind of topics. So yes, that's a very current topic, and it does vary a little bit from device to device how much buffering is built in for accommodating, late arriving audio or late arriving video, or for that matter, audio that's way too early or video that's way too early. Those are really the same thing, right?
Okay, our final question for this break is from Nick. Do ST2110-20 packets belonging to the same frame have the same PTP, RTP timestamp?
Packets that belong to the same frame or field in the case of interlace have the same RTP timestamp because they are presumably captured at the same point in time, ignoring things like rolling shutters and so forth. All the pixels of a frame or a field in the case of interlace have the same RTP timestamp.
Perfect. And we will hold the other questions. Nick says perfect, thank you as well. So we'll hold the rest of the questions until the end. And so please proceed.
Okay. Well, 2110 is, like I said, it's published. There's, some implementation questions always, and, work ongoing on getting everyone's implementations, perfected. But really, from a customer perspective, the question is, how do I make a routing system out of it? What are the other parts? Because 2110 just says how to put your pixels on a wire, or how to put your audio samples on a wire, or your ANS packets. But really, we want to make television. So a few other pieces round out the set. The Advanced Media Workflow Association I mentioned earlier has a couple of specifications that were built in harmony with the 2110 activities. So while we were working on 2110 on Thursday mornings, we were working on ISO 4 on, I think it was Wednesday mornings. The ISO 4 describes how devices join the system. So if I'm building, say, a control system, I need to know where all the little, 2110 devices are. So in the ISO 4 world, a device wakes up and it finds this registry in the network and it registers. It's really not a very complicated standard. It describes this very simple function of how does a device, find the registry, how does a device register itself, and that includes details like I generate this many audio streams, I generate this many video streams, how those audio and video streams relate to each other. Do they group together in a organized way? So it's a really necessary piece because otherwise you have to kind of keep track of everything by hand. And we've all built systems where we have to keep track of everything by hand on a giant spreadsheet and wished that there was an automated way. Well, ISO 4 is that automated way for devices to register themselves into the network. It also, once you have a live registration system, you can do things that are really hard today. Like you can have a camera that, sometimes you use it in Studio 1 and sometimes you use it in Studio 3. And so when you take it and you unplug it from Studio 1 and plug it in Studio 3, in the IP world, it probably will have different IP addresses and so forth. And so this live registration methodology lets us deal with that. And the same is true not just with cameras, but happens all the time with other shared equipment, monitors and prompters and so forth. Can, because it's a live registration environment, if you move one down the hall or over to a different stage and plug it in over there, it registers into the network and it makes itself ready to go. It's a really nice attribute that you don't get from a spreadsheet and a pencil. Now, IP routing is different than SDI routing, right? Because in SDI routing, you have a big crosspoint matrix and all the action happens in that crosspoint. So the control system tells the crosspoint what to switch, the crosspoint does it, and the receivers are just at the end of the wire. They eat whatever bits show up. And so that's the SDI world. We've lived in it for years. It had an elegant simplicity that the receivers could be quite dumb. In IP, it's different. In IP, the receiver is involved in the switching. And this just has to do with the nature of the protocols and the nature of how we're using IP networks, that the control system to switch a signal actually tells the receiver what signal it's going to get, including not just things like its multicast group, but also technical metadata that it needs, like the resolution, whether it's HDR or SDR, whether it's 422 or 444, all that kind of stuff. The receiver gets told that, before it gets the first pixel. And so it can be ready to receive. And then the receiver ultimately is responsible for how it switches to that signal and how it transitions the image. So the receiver can ask the network for the new signal using the normal mechanism for multicast, the IGMP joins. And then the network provides that new signal in the normal network forwarding logic way. But it's very different than SDI, because in SDI, the receiver didn't have to do anything except eat what came to it. In IP, the receiver is a little smarter. The receiver is involved in the switching. Now, to make that happen, then we needed a way to talk to the receiver. But first, let me dwell on the other points. Sorry, slides are in a different order than I expected. So whether it's SDI or IP, generally either a human or an automation system makes a routing system kind of request. It says, take camera 7 to monitor 3. And then something happens, presumably the route happens, and then the control system gets back to that human or that automation system and says, hey, monitor 3 is getting camera 7 now. And so, the operator initiates the action, the operator gets a status back that says, yep, I did that. And that's the human interface to the system. Now, underneath, you've got this blue box called the routing control system. And you say, well, what does it do? Well, what it does is a couple things. It manages grouping of things. So if camera 7 really means, a video from camera 7 and some audio from some microphones that are mounted on camera 7 and maybe some other data that came along with it, maybe there's PTZ data or something that has to come with that. The control system understands how all those parts relate to each other. The control system also is the thing that knows that that one's called camera 7. That name camera 7 is assigned in the control system. And of course, monitor 3, same thing. So ultimately, the control system is what translates that operator action of taking, say, camera 7 to monitor 3 into whatever it has to do to make all the parts of it happen. Now, in SDI, it would make cross-point takes into traditional cross-point routers. But in IP, it's a little different. It has to talk to monitor 3. So in our example here, the control system takes the human request and then says, hey, monitor 3, switch your video to this new multicast group. And by the way, that's going to be a 1920, 1080 interlaced 422 10-bit blah, blah, blah signal. And of course, then dutifully, sometime later, says, hey, by the way, I did that. And that I transitioned to that new signal. And of course, then the control system has to inverse translate that back into, oh, well, I heard that from monitor 3, and that's the signal from camera 7, so I'm going to signal back to the operator that all got done. And then if you look one step further down the chain, of course, monitor 3 then tells the network through its media interface, hey, I want to leave that old group and I want to join this new group. Or maybe it does that in the other order, depending on the nature of its internal construction. And then likewise, the network responds and says, okay, I'm going to stop the group you're stopping and I'm going to start the group you're starting. And so this sequence of events is very different than SDI. But from a operator standpoint, it's take this to that, boom. So as you can see, this communication between the control system and the receivers is kind of important. And that's where we talk about AMWA ISO 5. So ISO 5 is an AMWA specification that tells the receiver what it needs to know. So a controller uses ISO 5 to tell a receiver the details of the stream it's supposed to take. And it's, again, a straightforward spec. The AMWA specs are available publicly. If you go to amwa.tv and, sort of poke around a little bit, they're out there for anyone to read and see. And the actual defining objects are stored on GitHub, which is typically used for software API kind of specifications. So one of the things that this ISO 5 relies on is something called session description. So you'll see when you read the 2110 standards that they spend probably a third to a half of the characters in each document are really about session description and how does a 2110 sender describe itself with SDP. And so all of this data about picture size and frame rate and colorimetry and sampling structure is carried in this thing called an SDP. This SDP is a standard, it's RFC 4566. It's a IETF standard, obviously. And so AML ISO 5 is the preferred way to communicate that SDP information to the receiver and to get it from the sender. So it's, they all go together. 2110 says how to construct the SDP, and ISO 5 says how to pick it up and drop it off. So these are all good parts, but at the EBU last summer, there was a lot of discussion in the EBU membership about the pace of adoption of some of these specifications and some vendor-specific issues of their first couple of 2110 rollouts. And in general, there was a call for there to be a systems document that somehow described how 2110, ISO 4 and 5, and PTP and so forth really fit together to make a working system, because the world needed certainty on some topics. And so this was a call to action. So action happened. An editor was picked, an ad hoc group was formed to pull together a system document that described how these parts really fit together. And that is JTNM TR-1001-1. And the JTNM is the Joint Task Force on Network Media. Its website is jt-nm.org if you're keeping up on your scorecard. And this document is available for free on the jtnm.org website. And it says just what I said, it's how all these parts fit together to build systems. Now, the EBU thankfully came up with this nice pyramid drawing to talk about the, their view as customers, broadcasters of the IP universe. And so, things like 2110 are up in the green top part of the pyramid. They're well-defined, everyone understands them. Timing and synchronization and sort of discovery and so forth are kind of the yellow parts where there's well-defined methods and everyone's starting to use them. And then, of course, there gets to be, more and more difficulty as you go down the pyramid of things being fairly vendor unique, configuration and monitoring, and of course, security at the, as well, of how do you make these systems secure, and what does that even mean exactly? Because security is something everyone loves to talk about security, but it needs some well-defined language to really have a good conversation. So in the JTNM drafting process for TR-1001, we took this pyramid as sort of our user requirements, if you will, of how the document, what are we trying to respond to. Now, as can't be a SMPTE meeting without having the age-old SMPTE phrase, what problem are we trying to solve? And I like to put the word customer in that sentence because in the end, our customers are what fund all this work. The problem that this document's trying to address is a customer buys a new piece of 2110 equipment and they'd like to have it working in their facility. And so what all do they need to do? And is it a reasonable set of things? And can we make it be a reasonable set of things? So what does -1 cover? It covers for some domain of use, what are the requirements on the devices and the environment they live in so that a customer can have a straightforward workflow leading to using the device. If it takes your 4 best engineers 3 days to get a new piece of equipment working, probably there's something wrong there. And so that's the goal of 1001-1. Now, you'll notice I keep saying 1001-1. The -1 document covers a lot of stuff. There's some things it doesn't cover, and we fully expect to have to do a -2 or a -3 going forward to address, the next level down of issues. So what's this domain of use? That's an easy one, because all these standards, 2110 and AMWA and so forth, were all written to be really, really flexible. So we decided to limit the domain that we're trying to address here to engineered facilities, which, I think we all kind of have a vernacular understanding of what we mean by an engineered facility, but specifically one with an engineered IP network. And of course, producing, packaging, or delivering television or radio built around these standards. So it doesn't cover, for example, if I am doing a remote news shoot and I just want to plug 3 things together and have something magic happen. This really isn't that. This is an engineered facility. Now, some terminology that we use. So we talk in this document about media nodes. Well, a media node is anything that creates or consumes 2110. And in some of the AMWA specs, we call those senders and receivers, but generically here we'll call them media nodes. And I use the word environment because a media node lives in an environment. So in the case of a television facility, that environment is the control networks and media networks that it's connected to, the IP networks that it's connected to. And also, importantly, there are some network services that exist in those networks. So the device can wake up and expect to find certain things or certain services available to it, like PTP. Now, straightforward workflow, that's the funniest one of the bunch. So straightforward workflow, we do expect that you need a human in the loop for a new device. People talk about, oh, well, everything should just be automagic. But really in a running television facility, typically if you get a new device, you want to at least assign a name to it so that, like, is this camera 37 or what is it, right? And then typically also you have to assign some permissions and some rights. And honestly, if a new device showed up in your facility, you'd like to make sure you know about it, and it isn't just something that, somebody ordered and plugged in and you didn't know. So that's the kind of human in the loop, straightforward workflow that we envision, that there's still, both permission that the device ought to be here and giving it name and identity so that it can be used operationally. So this is our kind of standard diagram we use to talk about the environment. Now, it's very media node centric, of course, and we talk about there being a control network and being one or more media networks, and then some network services like PTP, DHCP, so forth, that a media node can expect to find. Now, standards, we got lots of standards. They're all kind of well known at this point, but the behaviors are where the work is here. How does a device wake up and know its place in the network? How does it know that it's in a new system or it's in the system it was part of when it was last powered up? How does it know some of the PTP stuff that it needs to know? How does it find that ISO4 registry? And how does it know what multicast addresses to use? Because there has to be coordination of that. Well, 2110 and ISO 4.5, as we mentioned early on, they're done. But this document really is about those behaviors and defining those and defining, how a device works with them. So the first one we kind of tackled, we said, well, how do you know your network details, right? Because you have to know your IP address on each of those networks. You have to know some information about the unicast routing environment. You have to know where the DNS server is potentially. So, well, anybody who's plugged their laptop in a hotel knows that DHCP is where it's at. So there's a thing called Dynamic Host Configuration Protocol, or DHCP. It's very well known and highly scalable and works in the IT environment at every company I've ever been at. The routers and the network equipment and the servers all support it. It's not like super secure, but it can actually be made quite robust. And so one of our first decisions in this drafting process is we said, well, we ought to use DHCP. We shouldn't, go invent something new. We should use DHCP. And that I don't think there was any disagreement on this topic. Everyone said, yeah, that would be smart. So the tech rec says use DHCP on all these network interfaces. The second problem was a little bit more interesting. As you say, as we make television equipment, customers have a requirement, a smart requirement, that equipment needs to power up and resume operation with its last stored settings. So whatever I was doing before, I got to come up and do that again. Or likewise, if operationally, sometimes operators like to blame a piece of equipment and then go in the back and power cycle it. Well, they expect it to come back up with all the settings it just had. And that's fine, mostly. But sometimes you have a new piece of equipment, which really wasn't in your plant before. So when it powers up, it's got whatever the factory was doing when it shipped. And sometimes you have rental equipment that, when it comes out of the box, it's got whatever settings it had at the last user. So those are cases we really have to understand and maybe do something smart. So it would be really helpful if a device could tell. And so we came up with this scheme where there's a system GUID, a global identifier in any system, and a device comes up and compares that against the GUID that it was running with last time. And that way a device can know really unambiguously, hey, I'm right in the rack where I was before and all my settings are valid, or hey, I'm new here and I need to wait for some instructions. So there's a whole couple paragraphs of the document that talk about what you do if you're new in town. The PTP system also has some parameters that you have to know. So every device has to know the PTP domain number. And if you're a device that has more than one port that you do PTP on, or potentially do PTP from, you have to know the announce timeout in order to make some good decisions across those interfaces. And the IEEE 1588 PTP doesn't have a mechanism to distribute that information to the clients. So they just have to know. So we defined a way to distribute the PTP information. So when a device wakes up, it can tell that, hey, in this network, it's PTP domain 57, and the announce timeout is 3. Otherwise, you just wind up writing that information on the whiteboard, and every time you fill in some new piece of equipment, you have to go into it and set those two things before it works. Now, ISO 4 and 5 have some things you have to do as well. So ISO 4 specifies either using multicast DNS or DNS service discovery for finding the registry. And MDNS works well on a local subnet, sort of a small network. But for most large network architectures where there's multicast routing involved, MDNS is defined on an unroutable range of addresses. So the decision was we really need to use DNS service discovery via normal DNS to have a reliable way to find the registry across different architectures of networks. So that's the recommendation we came to, is that media nodes will use multicast or use unicast, plain old DNS service discovery to find the registries. And DNS has been around for many years, almost as long as DHCP. DNS is how your browser finds google.com. I mean, it's not a new technology. It can be made quite reliable and quite robust. And in any given media enterprise, there's somebody in your IT team that knows all about DNS and how to configure a DNS server. So this global information, things like the PTP stuff or the system ID, how do you distribute that? So we made a new API structure. This may have an AMWA number at some point in the future, but right now it's defined in the TR. And so you look up in DNS service discovery and find this thing. And then based on the IP address and port number you got from DNSSD, you do a HTTP GET and you get this structure. And the structure includes an ID, that is the system ID, It includes a version, which is like a timestamp. Has a couple other descriptions and things which aren't that interesting. And it tells you things like the PTP stuff you need to know. The ISO 4 has a system heartbeat that you kind of need to know. And we also put in some definitions for log servers. So devices can know where to send logging information if they're going to do that. So the TR defines this, this structure for all this global information. Now, the last big thing we had to wrestle with was multicast address allocation, because every system we've deployed so far with 2110, the multicast addresses have been manually allocated. So there's a big spreadsheet. There's a pattern that says, 239.room.rack.something, or every facility has kind of a different way they want to organize the address pattern. And that works. I mean, it's tedious, but it works. But it is a bit tedious. So there is an RFC 2730 called MADCAP that describes how to allocate multicast addresses in an automated way. But the more we looked into it, it has a lot of limitations, and we ultimately decided it had too many limitations. ISO 5, remember that, ISO 5 actually has a mechanism for the controller to tell a sender what addresses to use if the sender supports it. Now, not all senders support it today, but it is a valid mechanism. And so the decision we eventually came to was that median nodes first need to support the whole range of allowed multicast addresses. I'll talk about why that is in a minute. And then second, that senders in particular, of course receivers too, but senders must support configuration of their transport information through ISO 5. So this way a controller can tell a sender, hey, this is the address you're supposed to use in this town. Now, this first bullet there about supporting the whole range of multicast addresses really gets to another problem we were seeing as we rolled out more implementations of 2110. And that was that different vendors of video and audio equipment were making different assumptions about, they could just use 239 dot whatever addresses or just use some other range of addresses. And we were starting to see, potential incompatibilities where you couldn't pick an address pattern that was actually usable by everybody. And these were all kind of arbitrary distinctions. They weren't really driven by a technical need. They were driven by some other non-technical kind of thought process. So we decided to go ahead and just make it a rule that if you're a media node, you have to support the entire range of allowed multicast addresses. Now, there are some in like the 224.000 and 010 ranges that you're really not allowed to use because those are used for routing protocols and other things that you can't interfere with. But the rest of the range, devices, media nodes have to support. Now, different networks have to, when you're a customer and you're building a facility, you may want to coordinate. You may want to say that, in my facility, I'm only going to use a certain range. And that's your right. That's you absolutely should do that. But this is really a requirement that the media nodes can't force you in that decision. That's a decision you make as a network designer, not a decision that a media node makes for you. So those are all the kind of main points of the document. Where we are is that this document was drafted by kind of an ad hoc drafting group. We followed the AMWA IPR guidelines because we had to follow some IPR guidelines. There was a pretty broad representation of the JTNM member organizations, included a good sampling of broadcasters and also, of course, equipment vendors. And so the document was developed and vetted through a process and then was eventually published. So this has been up online at jtnm.org for some time now, 6 or 8 weeks at least. And it's, we've received good feedback. We have had people ask clarifying questions, and we're collecting a little core agendum. So we probably will have a little, minor update to it with some, little small bits that people have noticed over time. We're kind of collecting on the side a list of things we could be clearer about or say a little differently. And then one of the objectives as we go through these interop events this spring is to, provide an environment that offers these network services so that people who are attempting to implement the TR can do so and can check it in an environment that has the DNSSD, has the ISO4 registry, has the DHCP servers, and so forth. Building an environment that people can test that their system actually works right. So that's kind of the meat of our topic for today. I'm going to suspect that there might be a few questions, and this is the time for them.
There are more than a few questions, yes. So I will read them quickly, and actually the first one is a verbal question, and it comes from Alan Mays. Alan, you should be unmuted.
Hi, John. I actually have a couple questions. First one is on IP version 4 versus IP version 6, and talking to various people in the group about how there isn't been anything that's set up for that. And the second question is on ISO 6 and 7 and where we are with those two standards.
Okay. So with respect to IPv4 versus v6, the TR does not say anything new about that. That was mainly a topic of conversation in the 2110-10, where we deliberated a long time. We designed the format of the bits and the length of the messages and so forth so that you could have an IPv6 header. And we designed everything to be capable of running an IPv6. But when it came right down to shoulds and shalls, it's currently written as shall support IPv4 and should support IPv6. And that's kind of where we got to on 2110-10. I don't expect we're going to change that in the one-year review, although anything could happen. But that's kind of a state of adoption. Typically, these media networks are private networks, so they're 10.10. Whatever, 10.000 style networks where there's plenty of IPv4 address space. And I think the comfort factors in industry is that we all understand IGMP and on-PIM and sort of the IPv4 multicast world, whereas MLD and the IPv6 multicast world, I think once we've done it a few times, we'll all say, wow, that's so simple. But there's just everyone's kind of standing at the edge of it and looking into it and saying, oh, let's just do the thing that worked last month. So that's kind of the state of 4 and 6. There's no new news there. As for ISO 6 and ISO 7, so ISO 6 is a network control specification. Nothing in this TR sort of requires or prevents you from having ISO 6 used as part of the network infrastructure. So the TR will work equally well whether it's a ISO 6 controlled network underneath or a engineered IP, IGMP and PIM network. Either way can work. So the TR doesn't require or prevent you from using ISO 6. And ISO 6 is now, it's published on the AMWA site, it's publicly available, and the committee is working through, what are the things they'll do in the next iteration of it, the 1.1 version. ISO 7 is, if you think of 2110 as having methods for video and audio and ANS data, ISO 7 actually is a method for tally information and event information. So it's hard to believe it's 2019 and we're still wiring Form C relays, but and so ISO 7 is a API that is really about how to modernize that event and tally information now that it's 2019 and we're supposed to have flying cars. Okay.
Thank you.
Very good.
I
Oh,
think
sorry.
the question about 07 was about the status of it. Is this right? That's Brad Gilmer.
What is the current status of it? I think it's a published spec. That's one of the things we're doing in the workshop next week.
Yeah, exactly right.
Thank you. Alan, did you have a quick follow-up question?
No, that's it. Thank you.
Great. Let's see, Mark. No, John. What happens when one has to perform address translation on PTP?
On PTP?
Correct.
I don't think one performs address. PTP is always sent on the same multicast group. There is no translation. It's always, PTP. There's a specific group that's written into the IEEE standard. If you're doing PTP on a layer 3 network, it's always the same multicast group. But it's possible that I've misunderstood the question. So if that didn't answer the question, please retype the question and we'll hit it more correctly.
Thank you. Patrick asks, can the registration work beyond the LAN, such as across the WAN?
Yeah, the ISO4 registry protocols are unicast regular things. So if you can reach the registry using IP, then you can register. Now, more broadly, the question is, can I do, say, 2110 systems over a wide area? There's actually a working group right now in the Video Services Forum that's attacking that very question. So if you're feeling bored on Thursday mornings, on the morning that the 2110 drafting group isn't meeting, then you can join that group if you're a member of the Video Services Forum. And we're attacking that exact question of what does it mean to do 2110 over a wide area network? How do we address the timing issues? How do we address the registration issues as well? But there's nothing about the ISO4 spec that limits it to a local area network. In fact, the only thing that was really limiting it to a local environment was that it, in some implementations, was using MDNS. And that's why in the TR, we've actually deprecated MDNS in favor of going to DNS service discovery, because DNS SD is unicast DNS and can work over a large-scale network.
Yeah, and Christoph asked a question that mentions MDNS. And Christoph says, isn't MDNS handy for small installations like EFP?
It is, and it's certainly useful there. The TR was really built around the domain of use of larger scale engineered facilities, and that's why the TR is more specific about using DNS service discovery, because then MDNS has a challenge that it doesn't propagate beyond layer 2. It uses one of those restricted multicast addresses we talked about, and those don't route. So even if you have PIM set up in your network, that doesn't mean that the MDNS will actually propagate from subnet to subnet. So for these engineered facilities that are the domain of use of the TR, we decided that DNS service discovery is the appropriate technology. But if you're in a different domain of use where you're doing, say, a news lash up or something, then yeah, the MDNS may be perfectly appropriate.
Okay, let's see. Well, before we take any more questions, Brad Gilmer would like to make a clarification about the use of the word interop. Brad, if you unmute, the floor is yours.
All right, thank you very much. Yeah, John, I just wanted to jump in here. One of the words that you used a number of times is the word interop with relation to events where we're getting people together in the industry. And that caused some discussion at the last EBU PTS seminar. I just wanted to clarify the fact that these are workshops, and they're opportunities for people to bring implementations and be sure that they work right and tweak the equipment to make it work better and so on. Of course, with the goal of achieving better interoperability, but there is nothing in the sort of activities that you have mentioned in this webinar that have anything to do with any sort of interop results that might be published or issuing of any kind of certifications or anything else. I just wanted to make that point.
Yeah, no, that's an important point, that there is other work going on elsewhere to actually look at certification of 2110 systems and so forth. But this, these events are really private events where people who are making equipment can go try the equipment with each other and figure out that, I read it this way and you read it that way, and decide over dinner which one of them is correct. It's critically important, if you're a customer, that the vendors have done this before the equipment's on your machine room floor. And so that's why we have these events. But yeah, they are more correctly called workshops. And we sometimes our linguistics aren't so perfect.
Yoshiaki-san asks, could you briefly explain how a receiver detects the frame boundary from an incoming packet sequence?
There's a bit that is called the marker bit that is set on I believe the marker bit is set on the last packet of the frame. And so for video, there's two ways you can tell if you're, where the frame boundary is. The first way is to look for the marker bit. And then the other way is that all of the packets of a frame or field have the same timestamp. And then presumably the packets of the next frame or field have a larger timestamp. And so those are both good clues to know where one frame ends and the next one begins.
Next question is from Paco. Is there any plan for a recommendation or standard to clean switch between streams, or a standardized definition for a clean switching mechanism apart from what some vendors already have, like, for instance, freeze one frame or use temporary double bandwidth during the leave join process?
No, I think the current view of, all these activities are sort of voluntary activities on the part of the vendors and customers to create standards. As I mentioned, sort of mid-presentation, how a receiver switches from one stream to the next is very receiver dependent. So some of them will, drop the old one and then clear their buffers and think about it for a while and then join the new one. And so visually it's kind of not perfectly clean, but there may be good reasons why they do it that way. Some of the test equipment, for example, does that so it can really perform a clean measurement of the new stream. Similarly, there are other receivers that are really designed to join the new stream and then, synchronize up and then do a clean and quiet switch over from the old stream to the new stream and then drop the old one. That does add, does require more bandwidth during the transition. But remember that bandwidth is only on the sort of access link to the device itself. It's the stream was probably already in the network somewhere. So most receivers that do that typically manage that bandwidth of the access link. And while you say, well, it's extra bandwidth, it's in practice the bandwidth. If you have, say, a 10 gigabit access link to a device, there's either 10 gigabits of idle packets or there's 10 gigabits of Ethernet traffic on it, but there's always 10 gigabits of something. So it is very device dependent, but I don't know of any activity that's trying to standardize some magic inside the network to do some magic switching there. There certainly have been demonstrations of that, but not really ever of methods that would scale to the number of streams that are typically used in a large facility.
Thank you. Dennis asks, are the APIs required for DNS-SD REST or SOAP?
Well, DNS-SD uses DNS as the API. So literally to resolve a name using DNSSD, you do a DNS query to the DNS server using the DNS protocol. It's just another record type in regular DNS. So these names would be defined in the DNS server, just like you'd define a static name for something, you can define a static service name. The AMWA APIs, ISO 4 and 5 and so forth, are all REST APIs with JSON.
Thank you for the clarification. Patrick asks, does AES 67 mandate the use of 239.0.0.0/16?
Boy, that sounds like a trick question. It may, and that may be a place where 2110 and this TR are more broad. In practice, I'd have to look it up, to be honest. I don't remember if that's if that was restricted in AES 67 or if it was a should. Sometimes in AES 67, there's a lot of things where it says should. But in a practical sense, we need devices to be more broad in their support of addresses because customers building networks have to coordinate multicast utilization across sometimes many different facilities. And so if we arbitrarily restricted the audio world to always be in a small range of multicast addresses, it would be untenable in a large facility system or large enterprise to have to do that. So that's why in the TR we recommended that devices need to support the whole range of legal multicast addresses so that the customer building their facility can then take advantage of knowing that this range of addresses is used in this city and this range of addresses is used in this building, rather than having it be a constraint driven up from some microphone or speaker.
Next comment, actually, not a question, comes from Michelle. Michelle says the TR initiative is excellent, great work, and a great presentation of it. Thank you. And thank you, Michelle. Next question. Let's see. Do engineered networks, as noted in TR-1001, accommodate geographically distributed endpoint sources that contribute to a central facility?
They certainly could, and they, if they're engineered, I think there is probably some point of scaling at which it's more wise to treat the facilities as separate facilities, and it may be related to PTP timing and how do you treat things as one large PTP domain or as separate domains. But certainly there's nothing in the TR that prevents it from being, applying it at very large scale geographically. But I think you may get into challenges if you had, tens or hundreds of milliseconds of delay between sites in trying to accommodate the actual logistics of that from the standpoint of delay matching and play out delay on devices. So there's probably a point at which there's other challenges will come in because of geographic delay, but the TR doesn't specifically say it has to be local or has to be global. It just we left it as the simple statement about engineered networks as opposed to ad hoc networks or undesigned networks.
Okay. And Brian asks, do those engineered facilities cover OB trucks?
Yes, certainly an OB truck is a very tightly engineered facility, at least an OB truck that works. In fact, I think even the specific language in the document gives that exact example of, an OB truck is an engineered facility.
Ah.
I'd have to look to be sure, but that definitely OB trucks are heavily engineered or do count as engineered facilities, fixed or mobile.
All right. Let's see. Dick asks, How would IS-07 work in practice? Would a production switcher send out a packet every time a source changed in the tally status?
I'm not an expert on IS-07, but yeah, I think that it's exactly like that, that the switcher would either consume or produce tally information depending on what the aspect is. So the switcher would produce an event message saying, the program bus has this now, or the, ME5 has this, or whatever, actions there are. And then a, centralized log, something would subscribe to that event notification and do something with it, like change a lamp or change a lamp color or something.
Excellent. Let's see. We're getting closer to the end here. Martin asks, would you give an overview of IS-08, please?
Sure. I know too much about IS-08. So IS-08 is relates to audio channel mapping. So IS-05 that we just talked about lets you tell a receiver to take a certain audio stream. But typically these audio streams have multiple channels of audio inside them. And so IS-08 is a API that in a standardized way tells, lets a controller manipulate the mapping of, or the mapping between those channels that come out of the audio receiver and whatever internally is consuming it. So instead of just saying, hey, I'd like to take this stream to this receiver, you can then, with the combination of IS-05 and IS-08, say, I'd like to take this stream to this receiver and do this with the channels that were inside it. Take this one to there and that one to there and ignore this one. So that's, in a nutshell, the IS-08. And it's available, free for download on GitHub, and it's a current active work item in the AMWA to perfect IS-08.
Thank you. Let's see. Martin actually posted this question at the very beginning of the webcast, and we held it to the end here. We do have a few others, however, but we'll do Martin's question now. Let's see. System resources defined in Appendix A include a system ID, which shall be assigned randomly and uniquely in each facility. How will these resources be defined, for example, by vendors, manufacturers, facility, and under what guidelines?
The beauty of UUIDs is that they don't have a central authority. There's not a central repository of UUIDs in the world. It's a typically 128-bit or larger magic number. So there's not a centralized authority of UUIDs. It's quite the opposite. In a facility, when you stand up the facility, you kind of pick a UUID. You shake your magic 8-ball of UUIDs and write it down, and there you go. But because so many things key off that, you really have to write it down in non-volatile ink on a really solid piece of paper and remember it, because if you change the UUID of your facility, then every piece of equipment next time it wakes up will decide that it's not in Kansas anymore. So it's quite important that whatever UUID you create, that you write it down well and keep it. But that said, there is no central authority of UUIDs. They are, it's a scheme where you make up the UUID and you trust the logic, the randomness of large numbers.
Okay, writing it down.
And in practice, collision of UUIDs, and they're used in millions of things, right? The collisions of UUIDs are so rare that I don't think there are very many documented cases of it ever happening in a way that mattered.
Thanks. Martin follows up. Thank you kindly for answers, and looking forward to integrating IP systems. All right, just a few more now. SMPTE friend Fred asks, when the control system makes changes for camera feed to monitor or production switcher input, does it also handle IFB, sync, tally, video return from the switcher output? In short, all of the disparate other signals?
Well, it certainly can. That's a control system topic, right? It's the same question applies whether those signals are done in SDI or done in IP or done in some other way. Typically, it's one of the jobs of a control system to keep, to organize those parts that are supposed to switch together so they switch together when they're supposed to switch together. But that really doesn't change for, with IP. That's always been a kind of a feature in the control world to say, these signals bundle together. And in fact, the signals in a hybrid plant could be a mix of IP delivered signals and baseband type signals that switch together. It's really just up in the control system that it has to, keep track that those are a bundle of things that I have to do something consistent with.
Okay. Let's see. Abdul asks, the abstract network diagram is too high level. Any advice on building the amber and blue network completely physically separated or virtually separated based on VRF?
Both methods have their places. Every 2110 system we've built has been somewhere along that continuum from, in some cases, two completely separate networks. In some cases, separate spines, but then have leafs that are a mix of the two in some places. It's one of the beautiful things about these IP networks is that it gives you a large range of trade-offs between cost and resiliency. So you can build a very, very resilient network, but you wind up with kind of two of everything. Or you can build a network that's somewhere between that and maybe you have separate spines, but some leafs that are consolidated or VRF split, as you suggest. All the way to, I have seen people build out just, single big switch and, hope it doesn't fail. I don't recommend that you do that way, but you certainly can. The beauty of the IP solutions is that you have a lot of trade-off you can make about cost versus complexity versus resiliency. Nothing TR says that you have to do it one way or another. We actually made the TR very flexible to accommodate, all the different ways that you could do it.
Okay, and our final question that we'll take today is from Mark. And it's actually about the workshop that you mentioned in February. Mark is wondering if you could provide information where vendors can get information about the venue.
Yeah, well, you can't just show up at the venue. You have to register. There's an MOU. There's some legal stuff. There's a whole lot of, it's not just a show up. So usually the information about it's been distributed through the BSF, through the AMWA, through the SMPTE as well. So if you reach out to me or to Joel or to Brad Gilmer, or any of us get you in touch with the organizers, and if you want to participate, it's always welcome.
Thank you, Brad.
Go ahead, Brad.
Yeah, just we do have an email address, info@jt-mm.org. That email address will go to Bob Rule, but it's just a handy shortcut address. And if you're interested in finding out more about the workshops and what the requirements are and signing up, that would be a great address to use for that.
Yep. Yeah, that's all I would have wound up doing is forwarding it to Bob. So yeah, save the step and do that. That helps everybody.
Thank you, Brad. And Charlie says thank you as well. So that's the last question that we'll take for today. Brad, thank you for your input. John, I'd like to thank you for an excellent presentation. And I'd also like to thank our guests. We had well over 200 people this time, and appreciate the verbal questions. Awesome participation. So thanks to all. Have a great day. If you are traveling anywhere, safe travels. Alan says thanks. This was very helpful. Fred says good show. As I said, Charlie said thank you. So take care, and we'll see you on the next SMPTE webcast. Bye-bye, everybody.